So today, two reasons it will be pretty hard. The first reason, very abstract. Asymptotic notation, very abstract. Second, we will use a lot of math to do the calculation. Yeah. Limit. Remember the last time L'Hopital's rule. Yeah, the same thing we will do many times. I will show you many examples. So, yeah. So that's the typical features in today's lecture. Yeah. All right. Before we start today, let me just summarize a little bit what we did last time related to today's lecture. Yeah. So the last time we tried to do one thing, very important, efficiency estimate. Estimate the efficiency of algorithms. Yeah. Then we try to look at the whole procedure about a typical algorithm. We notice one important property. So that is, when the problem size relatively small, that efficiency number is not very important. The reason is the overhead will distort that efficiency number, make a lot of distortion on it. Yeah, overhead part. Yeah. Typically, when you set up environment, prepare for your data, you need to spend a lot of time in your program for the overhead part. So that overhead part will make a lot of distortion on efficiency number. So we don't want to look at that part, initial part, when we try to measure efficiency. So we want to mainly focus on the case when the problem size is very large. All right. So when we look at typically the large data size part, because that is the hard calculation part. At that part, our computation time could be very long. So that's our concern. Right? Yeah, small size part, the computation time really fast, so we don't worry. Yeah, so we don't worry. Yeah, so that's the main reason. Yeah, but in order to describe the efficiency measure when the problem size is very large, we need to carefully design some efficient notation. Very efficient, concise, but very powerful notation. That is the reason asymptotic notations. How about that? Yeah, so that's the short summary from last time. Now let's do the continuation. Yeah, this asymptotic notation. All right, yeah, all right, yeah. Oh. Yeah, what's wrong? Yeah, let me test it a little bit. Oh, yeah, doesn't work. Still not working. Yeah. Let me just shift a little bit. let me off it. Oh, freeze. Oh, stop. Oh, yeah. PowerPoint. Again. Oh, good. This time it works. Restart it. Yeah, basically just restart it. Yeah. But let me start sharing again. Yeah, because I stopped sharing. Yeah. Oh, yeah. Probably next time I need to connect my remote control before I share the screen. Yeah. All right, so let's continue. Yeah. All right. Good, it works. All right. Yeah. First topic, limits of two growth functions. The question, how do we describe limits of two growth functions? Basically, the ratio of two growth functions. Yeah. We calculate the limit when the problem size n goes to infinity. Yeah. When we do that, so here we consider the general case, very abstract case. When we use the limit to compare two growth functions, how many cases do we have? We want to look at all the possible cases. The limit value, all the possible cases. Yeah. So let us recall, use your calculus background. Yeah. When you do this, how many possibilities do we have? Yeah. So let me list all the cases. Yeah. You can see, basically we have four cases. We try to cover all the possibilities, four cases. The first, limit equals 0. Yeah. That's simple. Second, C, non-zero constant. C, it's a non-zero constant, so I put a C. Okay. Third, infinity. Infinity. The last one, other than these three, we still have another case. Other, what's that other? Yeah. Yeah. The limit does not exist. How do you know the limit exists, right? Nobody can guarantee that. Sometimes the limit does not exist. Yeah. Sometimes you may ask, I cannot imagine the situation when the limit does not exist. The limit does not exist. Well, I cannot imagine. Okay? Yeah. Yeah. Here, I may like to give you a simple example. The limit does not exist. All right. Yeah, let me just change the color. All right. First, let me just show a simple sequence. Limit does not exist. 1, -1, 1, -1 to the infinity. This pattern repeats to infinity. There is no limit for this one. Okay? No convergence, right? Up and down, never converges to one fixed number. Not 0, and it's not infinity. Not the first case, not the second case, not the third case, other. All right? Does not exist. 4 cases. All right. So now, let us look at all these cases and try to put the categories, try to create categories for these cases. Yeah. So let us do simple discussion. The first case. All right, so here, look at this ratio of 2 growth functions, f of n, g of n. So we compare which one grows faster, all right? Slower, yeah. So to talk about that, we use a terminology, order of growth. Yeah. The f function grows with certain order. So we call it order of growth. Yeah. For example, square order, for example, right? Cube order, fourth degree, right? So that kind of order. Logarithm, right? Logarithm also order of growth. So things like that. So we use this concept, order of growth. So basically, we calculate the limit of the ratio of these two functions. We compare their order of growth. We do the comparison. Which one has larger order of growth? That means that function grows faster. All right, so for the first case, you can see the ratio goes to 0. That means the denominator function grows faster. Yeah. Because eventually, when the problem size is really large, the limit goes to 0. The ratio goes to 0. Yeah. 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 So the computation, you see the result. Yeah. Yeah. So that one we can easily see order of growth of f of n less than order of growth of g of n. Yeah. That's the case 1. Yeah. Then for other cases, let's look at other cases. All right. Case number 2, constant c, non-zero constant c. Okay. Yeah. Yeah. Let me put since I put it here, let me just write non-zero constant. For our algorithm problem, we should put greater than 0. All right? Yeah. But look at that. The reason, in our algorithm context, we do not consider ratio negative constant. The reason is very simple. Efficiency number, basically the number of operations, right? Yeah. F of n, g of n, we use them to represent number of basic operations. That number, how can you make it negative, right? Yeah. So that's why I say in math we allow C negative, right? In math, if we just talk about, general math, then C could be negative. But in our algorithm context, we don't have that meaning, right? Not meaningful. Yeah. All right, so here I put greater than 0. Now, positive constant. Yeah, we just say positive constant. All right. So then, for the case number 2, if the ratio, the limit is a positive constant, no matter what the number is, 0.1, 0.00001, it doesn't matter. The value of C doesn't matter. We will say these two functions have the same order of growth. Yeah, even extremely small number, yeah, because based on our intuition, we feel, f of n over g of n, the limit equals 10 to the negative 7th power. Very small. We like to say, g function has higher order of growth than f of n, but based on our definition, it's not. Okay? The constant, the positive constant, its value is not important. Remember, you may ask me why. Remember the last time when we do the ratio, f of 2n over f of n. Remember the last time, let me put it here. We look at f of 2n over f of n. We look at this ratio, the constant cancel out, right? The constant cancel out. Yeah. So that's why we only care that constant is non-zero. Other than that, the value after cancellation, not important. Yeah. All right. So I hope you understand this case number 2. Same order, okay? Order of growth. Yeah. Then case number 3, you can see f of n. Yeah, because infinity, the ratio when n goes to infinity, this limit is infinity. Yeah, so you can see, naturally you can understand f of n grows much faster, right? Infinity, right? So we can say order of growth of f n greater than order of growth g of n. Yeah, that's the first three cases. How about number 4? Now we are at the number 4 case, other. Yes, other. Number 4, the limit does not exist. If we do the limit calculation, we have to stop somewhere. After we detect there is something wrong, we have to stop the calculation. It does not exist. So then, the limit calculation method will give us problem. We have to consider a different method. Yes, we have to consider a different method in that situation. Okay, yes, all right. So we need a new method for case number 4. New, non-limit method. Yeah, let's say non-limit method. We have to change the course. That happens frequently in the real world. When we try to solve a real world problem by a special method, if we get stuck, when we get stuck, we have to change our method. Use a different method. Yeah. Here, that's the case, so we need a new method to solve the problem. Okay, all right. Yeah. All right. Objective for, yeah. Now, for this new method, all right. So here, look at our situation right now. We want to compare order of growth. And we assume the ratio of their limit does not exist. Yeah. Here, we need a special method to help us still find the answer about the comparison result of their order of growth. Yeah. All right. Yeah, so that's the goal. That's what we are going to do. Yeah, later we have that method. Yeah. All right. So let's put it on hold a little bit. All right. Yeah. So we will answer this question, yeah, later at some time. Yeah. So let us go to another question. Yeah. We need some notations to represent these, let's say, 3 cases. Yeah, because this one, we need to answer it later. The answer still not easy to see at this point. Yeah. So let us look at the first 3 cases. Yeah. First 3 cases, we want to find some compact notations. Yeah. Why? The reason is because if we want to talk about these 3 cases, do we want to say words long, relatively long, right? So we don't want to say every time we say, a lot of words. Yeah, not a very efficient, right? So in this situation, we like to introduce some new notations. When we use those new notations, we do not need to say a lot of words. We just apply notations. Then people in this field can understand immediately. What's the meaning? All right. Yeah. The first notation, when order of growth of f of n less than order of growth g of n, we say f of n belongs to little o. Look at this symbol, little o of g of n function. So what's the meaning little o? Just notation. Okay? The meaning means this limit of the ratio equals 0. That's why. But it's not 0, it's a little o. Yes, we use the little o. Yeah. In math, notation is very important. Good notations can make our thinking much better. Notation help our thinking. Yeah. Little o notation. So this one, the first one. Yeah. The meaning, yeah. So you should go back to the limit case and order of growth case. Yeah. In your mind, yeah, you have that information. Number two, big theta. Big theta, when they have the same order of growth, we write this notation. F of n belongs to big theta of g of n function. Yeah. So that means their limit when n goes to infinity, positive constant, and they have the same order of growth. That kind of meaning. All right. The third case, little omega. Little omega. All right? Yeah. Order of growth greater than of fn, greater than g of n, we use little omega. Okay? Yeah, pretty abstract. Pretty abstract. Yeah. All right. Here, so let me explain a little more about these three notations. Yeah. And we do a little more understanding on these three notations. All right. These three are our most important three asymptotic notation. We call asymptotic notations. Yeah. Yeah. Approximate. Yeah. Not very precise. Asymptotic. Yeah. And we have more actually. Yeah. Later when we have chance, we may go to a few more, but these three, the most important three. Yeah. Other cases we rarely use. Yeah. Sometimes we may use a little bit. Yeah. For example, little o, so we have big O notation, right? Big O notation. Yeah. Little, big theta, we have little theta notation, right? Yeah. Little omega, we have big omega notation. Yeah. So you can see, another three, the meaning just the opposite. Yeah. But we rarely use them, so I may not go there. Yeah. Only when I use one particular notation, then I explain the meaning there. Yeah. All right. So that's one explanation. Another one. Yeah. Another one. This notation, when we use math understanding here, f of n is a function. In math, what do you mean f of n belongs to? Belongs to this little o of g of n. What is the mathematical object here? Right? In math, we may like to understand really precise the meaning for each notation. Mathematical object, what is that? Right? Yeah. Here, this object in math, it's a set concept. In math, you know the set concept, right? Yeah. So that one is a set. Set concept. Okay? Yeah. So this is an element, right? F of n, a function. We treat that function is an element in the set. So this notation belongs to or is contained in the set. An element in the set. That's the meaning. Okay? Yeah. So later you will see, when you see asymptotic notation expressions in your mind, you will have, oh, those are the sets in math. Yes. Yeah. So you will have a little better understanding. Yeah. If it is a set, we can use properties of set when necessary, right? Later, yeah, when we try to understand the working details, we may need to use the properties of set. All right? Yeah. I will explain. When we go there, I will explain what kind of properties we need for a set concept. That's discrete math. All right? This class, in the prerequisite, we have Math 3000, that's a big prerequisite for this class. Discrete math. I will use a lot of knowledge from discrete math. Okay, so this is one set concept. And this is one. Yeah. All right. Next. Now we get to this case we need to answer. All right, does not exist, but we want to compare how the method is using upper bounds and lower bounds for comparison. Upper bounds, lower bounds. When you see upper bounds, lower bounds, in your mind, you can imagine the basic mathematical tool we use, inequality. How do you do the upper bound, lower bound calculation? Using inequalities. Here, we use a lot of inequalities. Yeah. All right. How? Yeah. The function g of n is usually a simple function. Yeah, g of n, growth function. Remember, how do we get growth function? We try to make it as simple as possible, right? We take the dominant term, then we remove the constant, or we just use the leading coefficient at 1. Yeah, we try to simplify it as much as we can. Yeah. So like n squared, n log n. So that's our typical GL function. Typical situation. But here I use usually. Usually means most of the time, but not 100%, right? Sometimes we do not have to take g of n as a simple function. Could be a complex function. It's okay sometimes, but it's rare. Yeah. We allow it, but in the real world applications, we rarely see that case. We rarely see that kind of case. Only theoretically on paper, when we do the math, we will handle that case. But in the real world, we rarely work on that case. Yeah. All right. The function f of n could be a complex function. Yeah, typically it's a relatively more complex function. Use some constant multiples of f of n, g of n to approximate f of n. Yeah, here. The third point is the main point about this method, using upper bounds, lower bound. That method, the main point for this method. Yeah. How do we set upper bounds, lower bounds for this f of n function? It tells us the way to set those bounds. What way? Using some constant multiples of g. Yeah, that's the typical way. Constant multiple of g. Yeah, so that will make this method a little easier. So we know what we should do. Yeah, the third point tells us. Yeah. All right, specifically, can we find two positive constants, C1, C2, such that C2 times g of n less than or equal to f of n less than or equal to C1 times g of n condition. Yeah. This inequality holds under certain condition. Yeah. But later we will really study that condition. Yeah. So here we just put it on hold. The condition is missing at this point. Yeah. We will come back to fix that problem. Yeah. So now you can see, because if we use inequalities, we never do the limit calculation. We never do the limit calculation. Okay? So in this case, even if the limit does not exist, we can still use the inequality way to do the comparison. All right? Inequality way to do the comparison. Yeah. We don't have to stick to that limit method. Yeah. All right. So two methods. You can see inequality method and a limit method. Yeah. All right. Now, big O notation. Yeah, here I talk about our fourth. Yeah, little o. Yeah, we talk about, but here big O. All right, big O notation. What's the big O notation? Big O notation, because after we introduce this inequality method, now we are ready to talk about other related asymptotic notations. Okay, yeah, big O notation. For a given function g of n, the notation big O of g of n, this time, represents the set of functions f of n that satisfy the following condition. There exists some positive constant c, and now I try to address the missing condition there. Yeah, missing condition there. Yeah. Some non-negative integer and 0 such that f of n less than equal to c times g of n. This inequality holds when n greater or equal to that n 0. That is the missing condition. All right. Yeah. That means, we know n means the problem size. Usually we say when the problem size is greater or equal to some fixed constant number, n0, some fixed constant number. Greater than that, passing that line, then we have the inequality. Before this line, we do not require that inequality. Okay? We do not require it. Yeah. Only after that line, the inequality is true, then we have the big O notation. Okay? Yeah. I hope you understand the subtle meaning here. Yeah. Yeah, pretty subtle. Yeah. All right. Yeah. And in our wording later, in many of my questions, when I talk about this condition, I will say when the problem size n is sufficiently large. Okay? The wording regarding this condition, we usually say when the problem size n is sufficiently large. Yeah, because in the real world, when you say when something is sufficiently large, people may ask you, what do you really mean sufficiently large? Right? Because it is very vague. Very vague. In different people's mind, the sufficiently large could be different. Okay? Yeah, for example, do you mean 100 is sufficiently large? Or 1 million is sufficiently large? Or 1 billion is sufficient? Can you say that? Yeah. You cannot, right? Because with respect to particular problem, for some problem, 100 is sufficiently large. For some question, 100 is sufficiently large. But for some other problem, 1 million is not sufficiently large. How about that? Okay? Yeah? So that's why this something kind of relativity theory, right? Some relativity thinking here. Yeah. So let me give you a simple example here. Yeah. If you look at this, yeah. Parenthesis, m minus 20 to 4. How about that? Yeah. Look at that function. F of n equals parenthesis n minus 20 to the 4th power. For this case, is 100 sufficiently large? Yeah, 100 minus 20, positive. Yeah, so you can use a, positive power function for f of n, right? Yeah, so look at that. So, because 20 already sufficient, a number greater than 20 already sufficiently large. Yeah, you pass some fixed constant number, that fixed constant number is 20 here, all right? Yeah, all right. Next, if I n minus 10 to the 7th power to the 4th. Yeah. When we look at that, all right, 1 million is not sufficiently large, right? Yeah, 1 million, because 1 million 10 to the 6th, all right? Here we have n you need to minus 10 to the 7th, 10 million. So 1 million not sufficiently large because you cannot overcome this, negative constant. Yeah. So that's why I say, if you look at the specific value, you cannot say if it is sufficiently large or not. You need to look at the specific function to tell you if it is sufficiently large, right? Yeah. So try to understand, the subtlety here. Yeah. All right. Now, based on this, I will create some comprehension questions related to this point, yeah, to check your understanding. Yeah. All right. So let's continue. Yeah. All right. Yeah. So that little n0 plays an important role. Okay? Yeah. So, all right. Yeah. And here, let me talk about this little n0 a little bit. Yeah. Here, yeah. When we select little n0, in that example, we can select 20. This example, we select 10 to the 7th. Okay? Yeah. So when we select, that means we have freedom to select, right? Yeah. So 20 there, 10 to the 7th here. We have some freedom to select n0. Yeah. But in your problem, as soon as you select it, you need to fix it. Okay? Give you freedom to make selection. As soon as you make your selection, stick with it. Do not change. Do not change when n goes to infinity. You never change when n goes to infinity, right? After you select n0, fix it. Then, we make n goes to infinity, you have that inequality. That's the exact meaning for that n0. You have freedom, but there is limitation, rule for you. You do not have unlimited freedom, okay? So you have limited freedom. Yeah. You make your choice at the beginning. Yeah. When you feel, but you have to do the math to tell you if that is sufficient or not. Yeah. If not sufficient, you may get trouble, right? You have to make sure it is sufficient. All right? Then you stick with it. When n goes to infinity, you always stick with it. That's the meaning of n0. Yeah. All right. Yeah. So later, I hope when I talk about n is sufficiently large, you will not ask me what's the meaning of that, because that's the whole story. Yeah. We spend a lot of time for that story. Yeah. Because if you ask me to explain it, I may need to spend half an hour, right? So I don't want to every time go through that half an hour. Yeah. Yeah. Oh, sorry. Yeah. Yeah. Something is wrong here. Yeah, let me fix it at a break time. Yeah. All right. Next, our next topic, graphs of asymptotic notations. In order to understand asymptotic notations visually, so let us use notations. First, look at a graph of big O notation. This is the one. We draw f of a function first. Okay? So the lower curve, suppose that is f of n function. Now, we want to use some upper bound for f of n. We want to use some upper bound to measure it. So what kind of upper bound we want to use? Here, in this situation, f of n belongs to big O of g of n. We use the constant, positive constant c positive, positive constant multiple of g of n as some upper bound. So we can find some positive constant c, c positive, all right? So make sure this little c is positive. Okay? That's the first one. Second, big omega notation. So here, let me explain. We have little omega, right? Little omega. The limit of f of n over g of n equals infinity. That's little omega. But similar to our big O case, we have some big O omega notation. So what is the big O omega? Definition of big O omega. For a given function g of n, the notation big omega of g of n represents the set of functions f of n that satisfy the following condition. Inequality. There exists some positive constant c and some non-negative integer n0. You can see environment setup the same as before. The difference is first this inequality. F of n has a lower bound. This is the lower bound. What kind of lower bound? Positive constant c multiple of g of n function. That is the lower bound form. And little o when n greater or equal to little n0. When that is true, we have that big omega notation. Okay? So that is the meaning. So you can see you can put all these things together. Upper bound, big O notation, lower bound, big omega notation. Okay? For the graph, we can draw the similar graph. This time, constant multiple, positive constant multiple of g of n is used as one of its lower bound. We may have many lower bounds, right? You can draw many lower bounds. So this one is one of its lower bounds. That's enough. That's enough. Okay? And this line, n0 line, doesn't matter. That means this part, n less than n0, that part doesn't matter. Doesn't matter. Why doesn't matter? Let me repeat another time. Overhead occur here. That's why it doesn't matter. Okay? We want to skip the overhead part. Okay? All right. Big theta notation. Yeah, big theta. Yeah, this time, think about, we have upper bound, we have lower bound. How about we put both upper bound, lower bound together, right? Big theta. Yeah. Upper bound, lower bound together. So, yeah. So this time, we repeat the same language, yeah, related to the environment, but we need to use two constant, C1, C2, two constant. So this time, lower bound C2 G of n, upper bound C1 G of n, yeah, and n0, sufficiently large condition. Okay, yeah. So now you can see, yeah. At this point, we have total 5 asymptotic notations. This big theta we used before. In our limit case, we use it, right? Think about limit case, we have the limit of the ratio equals non-zero constant C, that corresponds to big theta. So here, we describe it in upper bound, lower bound way. So we describe big theta notation 2 places. Limit language, inequality language, 2 different ways for big theta notation. So total, here at this point, 5 asymptotic notations. Yeah. All right. Yeah. Any question at this point? Yeah. All right. Yeah. The graph, yeah, straightforward. Right? For the upper bound, lower bound. Yeah. So pretty straightforward. Yeah. Okay. All right. Next, examples. Yeah. Yeah. After I talk about the abstract concept for asymptotic notation, I need to give you many examples. Yeah. First, let us do a few simple examples. Then we take a break. After we come back, we will do a few more relatively hard examples. Okay? Yeah. Simple examples first. Yeah. Our first example, very simple. Show that n plus 2 belongs to big theta of n. So simple. How do you show it? Yeah. If you go back to the 2 different ways we use to describe big theta notation, you have 2 different ways, right? One limit way, another inequality way. Yeah. Here the limit way is very simple. Yeah. If you use limit way, you can get the answer immediately. Okay? Yeah. For example, the limit way, you take limit n goes to infinity, n over plus 2 over n, when n goes to infinity equals 1. You calculate the limit. 1 is a non-zero constant. Then you can say n plus 2 belongs to big theta of n. That's the limit way. Yeah. Straightforward, very simple. Yeah. Then for the inequality way, yeah. Here, I just want to show you the inequality way. Upper bound, lower bound. You need to find C1, C2, upper bound, lower bound. Okay? Yeah. So let's start. We want to estimate n plus 2 function. Yeah. We want to find appropriate lower bound function and upper bound function in the form of positive constant multiple of n. Yeah. So what is the simplest positive multiple of n as the lower bound? Just n, right? You drop 2. That's simple. Lower bound, just n. 1 times n. That constancy is 1. 1 times n. Drop 2. Yeah. So you get lower bound easily. How about upper bound? Constant multiple of n greater or equal to n plus 2. And there is a n0. There is a hidden n0 parameter you need to fix. Okay? Yeah. All right. Yeah. So for the lower bound, it is true, yeah, because we consider n greater or equal to 0. Yeah. Everywhere, n greater or equal to 0. All right, yeah. Yeah, so here it tells us C2 constant is 1. Yeah. Then we work on the C1 constant. Yeah. Let us change this expression to n plus n. How about that? Replace 2. 2 is a fixed constant. Replace 2 by n. Do we make this expression larger? When we do the replacement, replace 2 by n, do we make the expression larger? Yeah, under this condition, when n greater or equal to 2, it is larger, right? Yeah, when n greater or equal to 2, we replace 2 by n, it becomes larger. Becomes larger, we use this function as the upper bound function. 2 constant multiple of n. Upper bound function. Okay? So lower bound function, upper bound function. C1 equals 2. C1 equals 2. And n0 for C1, for C2, lower bound side, we only need n greater or equal to 0. For upper bound, C1, we need n greater or equal to 2. But we need both, right? We need both, so we select this one. N should be greater or equal to 2. Then both conditions true. Yeah, yeah. All right. So at the end, we set our n0 equal to 2. Yeah. So you can see our method number 2. You need to do a little more math work here. When you do the math work in your mind, you need to find 3 constants. 3 constants. C1, C2, and n0. Lower bound, upper bound, the condition line. n0, that condition line. All right? Yeah. Sufficiency line. We can also call sufficiency line, right? Passing this line, it is sufficiently large. Before this line, not sufficiently large. Okay? Yeah, we can simply call it sufficiency line. All right? Yeah. Yeah. So for the second method, you need to find 3 constant. Yeah. C1, C2, n0. Then, why I emphasize this a lot? Because this kind of questions I will give in your homework and the tests as a full solution type problem. Full solution, you need to write a full solution. Yeah, in this way, all right? In this way, okay? Yeah, all right. Second example. Yeah. This time, n cubed belongs to big omega of n squared. Big omega, lower bound, right? C multiple of n squared can be used as the lower bound for n cubed function. Now, first, understand that meaning. Then we can work on it. Okay? Yeah. Do we have this inequality, simple inequality, n cubed greater or equal to n squared, when n greater or equal to 0? Yes, we have. You have the constant c equals 1, and 0 equals to 0. And you don't need to worry about the upper bound. When you see big omega, you do not need to do anything for the upper bound side. Yeah. Nothing, okay? All right, yeah. Only 1/2 of the work for the big theta case. Yeah, 1/2 of the work. All right, we still have a few minutes. Let's do another example. Example number 3. Yeah. This time, parenthesis, n plus 2 cube belongs to big theta of n cube. All right, big theta of n cube. Yeah. Yeah. How to find upper bound, lower bound. Right? Yeah. Lower bound, yeah, similar to that. Right? We just drop the constant term, we get a lower bound. Yeah, easy and fast. N greater or equal to 0. Okay, yeah, the line, yeah, the starting line. Yeah. C2 equals 1. Yeah. Upper bound side this time, can we do the similar thing here? Replace 2 by n, right? 2 by n. So we just do this similar thing. Replace 2 by n, we get 2n for that condition. N greater or equal to 2. Yeah. After we get 2n, inside the parenthesis, when we take the cube, then we take the cube. So we get a times n cube as the upper bound side constant. Constant C1 equals 8. All right? So you will have C2, C1, and N0 equals 2. Yeah. So we find the answer for this question. Yeah. All right. Yeah. So here, at this point, I like to make some comments here at this point. Yeah. After you understand this example, it's pretty easy. Doing this way, pretty easy. Yeah. But I like to tell you, many students, when I give them similar questions in their homework assignment, what they do, yeah, let me tell you what they typically do. They expand n plus 2 cube function, right? Many terms, n cube plus 3 something, long, right? Pretty long. Expand that. Then after they do estimate. Much harder, okay? Much harder. Because a lot of work, okay? Many terms, many coefficients when you want to do estimate. Yeah, okay? Although it's not wrong, but very messy. Very messy, yeah. So after you learn this method, not messy, right? Not messy. Simple, fast, neat, yeah. So I recommend this way. Not the expansion way, okay? Expansion way. Expansion, because in my homework, I give the exponent number to 5. N plus 2 raised to the 5th power. When you do expansion, how hard it is. Think about that. If you do not use calculator, if you do not use symbolic math software, if you write it on paper, how long will it take? Right? Think about that. Not efficient, right? But here we don't do the expansion, right? We don't do the expansion here. Yeah. Yeah, so you can see a good method, bad method, the difference is big. At least when you work on your homework questions, you can save a lot of time. They may spend hours to do that kind of work, right? When they do that kind of calculation, they may spend hours. Because after the expansion, how to go to the next step, it's still very hard. Think about that. After the expansion, lower bound easy. You just take the first term. That's lower bound. But how about upper bound? Upper bound expansion, you have many, lower degree terms. How do you estimate lower degree terms? Think about that. Okay? Yeah. So don't take the bad way. Okay? The bad way, very messy. Yeah, but yeah. All right, so that's my comments. Let me stop here. Yeah. Although 2 minutes, yeah, let's go to the break time. So when you come back, we will work on some